In that last video, we took these two polar curves, the cardioid and the circle, and we calculated the points of intersection. So as a quick reminder, we found that this was a point where theta equals 2 pi over 3, and this was a point where theta equals 4 pi over 3. And we also have the pole, but we found that they hit the pole at different theta values. So that's going to be significant when we're creating the integrals that we are going to use to find the area of each of these regions. Now, when I say each of these regions, we basically have three different types of regions. We have the area inside the circle, but outside of the cardioid. That's this crescent shape over here. Maybe I'll shade that in green. And then we have the area in both of them. Maybe I'll shade that in purple. That's going to be inside both the circle and the cardioid. And then we've got the area of the region that is inside the cardioid, but outside of the circle. So that's what we're going to try to find now. Okay. So I think it's useful to watch the animation for how these graphs are created. Notice that when theta starts at 0, the circle is way over here and it's going through quadrant 3 while theta is going through quadrant 1 angles because r is negative, while the cardioid is going through quadrant 1. And then they both go into quadrant 2 when theta gets to be pi over 2. And notice what happens right here. They intersect at 2 pi over 3, which is what we calculated. And that's an important point because watch what happens. Right now, from theta equals pi over 2 to theta equals 2 pi over 3, the blue curve, the circle, is closer to the pole, and the cardioid is farther away from the pole. But as we complete that graph, we see that it changes to being the cardioid being closer in and the circle being farther out. This is an important boundary line that we're going to have to pay attention to. Okay. Furthermore, notice that during the second half of this rotation from pi to 2 pi, the circle isn't doing anything. We've already completed the circle, but we are completing from pi to 2 pi. We're completing that second portion of the cardioid. And we see that that other point of intersection down there at 4 pi over 3 is also what we were expecting. So anyway, keeping that in mind, we should be able to figure out all of these different areas. So for example, we have the area inside the circle but outside the cardioid, the green shaded region. So it should be fairly clear that as we're creating this green region, theta is going from 2 pi over 3 all the way around to pi, and then all the way around to 4 pi over 3. And we can just double check that in our animation. If we start at 2 pi over 3, oops, oh, too far, dang it, undo. Control Z is a godsend. 2 pi over 3. All right, so that's when we're about to start creating the crescent. And then we go up to pi, and we've created half of the crescent. And then if we go all the way down to 4 pi over 3, we're going to complete the crescent. But probably we're just going to go from 2 pi over 3 to pi and then double it. Remember, that's a nice trick. So from 2 pi over 3 to pi, that's going to give us that top half of the crescent. So if we integrate 1/2 the integral from 2 pi over 3 to pi of just the circle, then we're going to find almost all of the circle, right? Of the circle, and the circle was -3 cosine of theta, if I remember that, right? And we're going to square that. Now, if I just do that, then I'm tracing out the circle from from this point around to this point. So it's almost all of the area. We're just losing this little bit of area here, this little bit of area there. Okay? But we don't want all of that. We want all this purple stuff to go away. So the area of that purple stuff is going to be the area bounded by the cardioid using those same theta values. So we're going to go ahead and subtract out the cardioid, which is 1 minus cosine of theta. And again, we have to square that to find the area. It's the 1/2 r squared theta. All right, so that's 1/2 r squared minus r squared, and then multiply that by theta. That would be the setup for this problem. That's actually half of the setup, right? Where we've got the top half, so we want to make sure we multiply that by 2, so we get the bottom half as well. All right, so that is an expression that will give us the area of the crescent. I think I'm going to go ahead and leave the calculation to you because I've done that enough, and you guys can check your work in a calculator. So then we move on to inside both the circle and the cardioid. That's going to be the purple stuff. The purple stuff is going to be a little tricky because I want you to think about the theta values required. Let's go back to 0 to 2 pi. Okay, cool. If we start at 0, we're not tracing out any of the purple stuff yet. The purple stuff starts roundabout right there. I've gotten some of the, whoa, I'm going too far. The purple stuff starts right here. This area right here is shaded in purple, right? This area, and I haven't really shaded it very well, but if we shade a little bit more in there, that's part of the purple, just like this is part of the purple. Okay, so we're actually going to require 2 different integrals here. The first integral is going to be finding this little bit right here, and that doesn't have anything to do with the cardioid. That is only the circle. So this is a little bitty part of the circle that we need to make sure we include. So that's going to be the integral from, well, where did this start, right? This started at pi over 2. We go back to here at pi over 2. That's when that little part of the circle starts, and then and then we stop using the circle at this magic point of theta equals 2 pi over 3. So just for that one little sliver of circle right here, we're going to integrate from pi over 2 to 2 pi over 3 of the circle. Circle is negative 3 cosine squared, and we'll square that, of course. And we don't forget the 1/2. And that's going to give us, again, just that little bitty sliver of the purple region. Okay? So that we're going to have to stop this integral and start a new one because the bounds are going to be different now. We're going to keep on going around the circle. That 2 pi over 3, that theta value of 2 pi over 3 is going to keep on increasing. But as that keeps on increasing, we are, again, this is the purple region right here. We don't care about the blue anymore. From 2 pi over 3 to pi, we only care about the cardioid, the red part, right? The red curve. So if I go from 2 pi over 3 to pi and just integrate the cardioid, so go from 2 pi over 3 to pi of just the cardioid, which was 1 minus cosine theta, 1 minus cosine of theta, and we'll square that. Don't forget the 1/2 out front, and don't forget the d theta. Those 2 different pieces are going to trace out the top half of the purple shaded region. And of course the bottom half is the same, so we'll go ahead and take that and multiply it by 2, which is nice because that's going to just get rid of all the 1/2s. All right, again, that's a setup, but do not solve. We can solve this. That's not the purpose of this video. So you can do that on your own and then check your work. All right, and then finally, we've got the area of the stuff that's inside the cardioid but outside of the circle. That's the stuff I shaded in with orange. That one's kind of interesting as well because it's going to be 2 different regions. The first region is going to be the stuff in quadrant 1. Now notice the circle doesn't ever go into quadrant 1. So we definitely don't have anything to do with the circle for this part right here. Okay, and if you need to see that animation, we can go back here and we can take a look. If we go from theta equals 0 to theta equals pi over 2, this chunk right here is part of what we're looking for. So again, that doesn't have anything to do with the blue curve. So that part's going to be just with the cardioid. So we're going to go ahead and integrate from 0 to pi over 2, the quadrant 1 stuff of the cardioid, 1 minus cosine of theta, is what we will square. And we've got 1/2, and then we've got the d theta. So that's all of the area of the orange stuff that's in the first quadrant. But then we also have all the stuff inside this little wedge right here. There's orange stuff right there. But notice that the orange stuff between theta equals pi over 2 and theta equals 2 pi over 3, the orange stuff has boundaries using the circle and the cardioid. Which one's farther out? Well, we already talked about that, right? The cardioid is farther out for this region, right? So from pi to 2 pi over 3, the red curve, the cardioid, is farther away from the pole than the circle. So this is going to be an awful lot like the integral we did on part A, where we subtract the bigger one minus the smaller one, but the bigger one is the cardioid this time. So we'll integrate from where we left off at pi over 2. We'll go to 2 pi over 3. Don't go any farther than 2 pi over 3 because that's where our orange shaded region stops. And we've got big radius minus small radius. So again, this is 1 minus cosine of theta squared. Whoops, don't need to close the bracket. Minus the circle, which is negative 3 cosine theta, and we're going to square that. And once again, this is going to have a 1/2 out front. And once again, I'm only finding with this expression the top half of the orange stuff. There's also orange stuff on the bottom that we need to include as well. Since it's the same size, we'll just double it. So I'm going to slide this over a bit so that I can include the multiply by 2. All right, so paying attention to your theta values is very important on this. Another thing, a nice thing you can do, if you felt like it, is you could take this 1 minus cosine squared and make an entire integral that goes from 0 to 2 pi over 3 of just the 1 minus cosine theta squared, and then subtract the integral of the circle going from pi over 2 to 2 pi over 3. That might be computationally a little bit easier to deal with. So I guess I'll write that down. That's alternatively, or I'll go ahead and get rid of the 2's. I don't know. I guess I'll leave the 2's so I don't do too many things at once. We'll have from 0 to 2 pi over 3 of the cardioid minus just the pi over 2 to 2 pi over 3 for the circle. Okay, so that, if you were going to work out this integral by hand, which I suggest that you do, that second one would probably be a lot quicker to do. Lastly, I'll leave you with this thought about checking your answers. Once you've got all 3 of these areas, you can play around with things. Like, for example, it would be pretty easy to check what the entire area of the circle is, because we have a formula that doesn't require calculus. Pi r squared, r is 3 over 2. So if we take the green plus the purple, we should get pi times 3/2 squared, or 9 pi over 4. Likewise, you can calculate the area of the cardioid by integrating the cardioid squared from 0 to 2 pi and then cutting it in half. And then if we take the purple plus the orange, we should get the same answer. So these are things we can do to just double check and make sure that our answers are making sense. And yeah, who doesn't want to know if their answer is right?